Combinatorics, Lecture 9, Problem Session. Problem 1. In a survey about beverage preferences, 100 people were asked whether they like tea, coffee or cola, and it was possible to choose more than one beverage. It turned out that 41 liked tea, 35 liked coffee, 43 liked cola, 21 liked both tea and coffee, 15 liked both tea and cola, and 12 liked both coffee and cola. 20 people didn't like any of these beverages. The question is, how many people said that they liked all three beverages? To solve this problem, let us introduce some notation. Let us denote by omega the set of people who took part in this survey. Let A be the set of people who liked tea, B the set of people who said that they like coffee, and C the set of people who liked cola. What do we know? We know from the formulation of the problem that the cardinality of omega is 100, the cardinality of A is 41, the cardinality of B is 35, and the cardinality of C is 43. Further, we know that the cardinality of the intersection of A and B is 21, the cardinality of the intersection of A and C is 15, and the cardinality of the intersection of B and C is 12. Finally, we know that the cardinality of the difference between omega and the union of A, B, and C is 20. Let us note that the union of A, B, and C is a subset of omega, and so the cardinality of the complement to the union of A, B, and C inside omega equals the cardinality of omega minus the cardinality of this union. And so we have that 20, so that's the amount of people who didn't like anything, is equal to the cardinality of omega minus the cardinality of the union of A, B, and C. And we know that the cardinality of omega is 100, so we have the equation that 20 is equal to 100 minus the cardinality of the union of A, B, and C, from which we can deduce that the cardinality of this union is equal to 80. Now we can use inclusion-exclusion principle to compute the cardinality of the union of A, B, and C. By this principle, we have that the cardinality of this union equals the cardinality of A plus the cardinality of B plus the cardinality of C minus the cardinality of A intersection with B minus the cardinality of A intersection with C minus the cardinality of B intersection with C, and finally plus the cardinality of A intersection with B and intersection with C. It is this later cardinality which we need to find, and we know all other summands in this formula. So if we plug in all the numbers which we know, we will get that 80, which is the cardinality of the left-hand side, is equal to 41 plus 35 plus 43, these are the first three summands, minus 21, minus 15, minus 12, the next three summands, and then plus the unknown cardinality of A intersection B intersection C. And from here, it is easy to compute that the cardinality of the intersection is 9. So our answer is there are exactly 9 people in this survey who liked all three beverages. This completes our solution to problem 1. Problem 2. Between 1 and 2025, how many integers are divisible by either 2 or 5, but not by 3? Solution. In order to solve this very particular problem with particular numbers, let us try to solve an auxiliary general problem. Let A, B, and C be positive integers such that B and C are coprime, so they don't have any common prime divisors. Let us ask the following question. Between 1 and A, how many integers are divisible by B but not by C? Let us start by finding how many integers between 1 and A are divisible by B. So what is divisible by B? That's B, 2B, 3B, and so on. And so it's clearly the number of such integers is A divided by B. But of course A divided by B doesn't have to be an integer, so we need to take the maximal integer which doesn't exceed this rational number A divided by B, And that's exactly the definition of the floor function. So the floor function is a function which assigns to a real number the maximal integer that doesn't exceed x. So there are the floor of a divided by b integers between 1 and a, which are divisible by b. Now, since b and c are coprime, they don't have any common prime divisors. If something is divisible by both b and c, it must be divisible by their product bc. So we have the floor function of a divided by b integers between 1 and a that are divisible by b. And out of these, we have the floor function of a divided by bc integers that are divisible by bc. So these are the integers between 1 and a, which are divisible by bc. So the answer to our general problem is that between 1 and a, the number of integers that are divisible by b but not by c, where b and c must be coprime, is the floor function of a divided by b minus the floor function of a divided by bc. Now let's use this. First of all, let a be the set of all integers between 1 and 2025 that are divisible by 2 but not by 3. By our general formula, the cardinality of a equals the floor function of 2025 divided by 2 minus the floor function of 2025 divided by 6. That is 1012 minus 337, which gives us 675. Next, let b be the set of all integers between 1 and 2025 that are divisible by 5, but not by 3. Again, by our general formula, the cardinality of b equals the floor function of 2025 divided by 5 minus the floor function of 2025 divided by 15. That's equal to 405 minus 135. This gives us 270. What we need to determine the cardinality of the union of a and b, and by inclusion-exclusion formula, this cardinality equals the cardinality of a plus the cardinality of b minus the cardinality of the intersection of a and b. So we already know the cardinality of a and the cardinality of b. Let's determine the cardinality of the intersection. This intersection consists of all integers between 1 and 2025 that are divisible by both 2 and 5, but not by 3. If something is divisible by 2 and 5, it is divisible by 10. And in fact, if something is divisible by 10, it is divisible by 2 and 5. And note that 10 and 3 are coprime. So we again can use our general formula and obtain that the cardinality of the intersection of a and b is equal to the floor function of 2025 divided by 10 minus the floor function of 2025 divided by 30, which is 202 minus 67. It gives us 135. And now we can plug in everything in our inclusion-exclusion formula and get that the cardinality of the union of a and b equals 675 plus 270 minus 135, and this is equal to 810, and this is the answer to our problem. Problem 3. A password is a string of 8 to 10 letters. Each letter can be either A or B, and it can be in either upper or lower case. And a valid password must contain both letters, both A and B, and must contain both cases. So the question is, how many valid passwords are there? Solution. Let us fix a length n, which is 8, 9, or 10. So these are the allowed lengths for our passwords. Each position of our string of n letters can be either lowercase a, uppercase a, lowercase b, uppercase b. So we have 4 choices for each position. So the total number of strings of length n with 4 choices for each position is 4 to the power n by the rule of product. Now let us analyze the strings which are not valid, so the forbidden combinations. Let x be the set of strings that have neither lowercase a nor uppercase a, so there is no a there. So the only two choices for each position which are allowed are lowercase b and uppercase b, so we have 2 to the power n such strings. Let y be the set of strings where we have no b, no lowercase b, no uppercase b. So the only two choices for each position which are allowed are lower and uppercase a, 2 choices, so we have 2 to the power n such strings. Let z be the set of all strings where we don't have any uppercase. So in any position we only allow lowercase letters, 2 choices for each position, 2 to the power n strings of this form. And finally, let u be the set of strings where we don't have any lowercase. So we only allow uppercases, 2 choices for each position, 2 to the power n such strings. Directly from the definition of this x, y, z, and u, we see that their union gives us all forbidden combinations. So the answer to our problem for a fixed length n should be 4 to the power n minus the cardinality of this union of x, y, z, and u. And we can compute the cardinality using the inclusion-exclusion principle. For this we need to understand the intersections of x, y, z, and u. If we intersect x and z, this means that we forbid one letter and one case. So what remains is only one letter and only one case. So any position has only one possibility. So there is only one element in that intersection. And similarly for the intersections of x and u, y and z, and y and u. So these 4 intersections are singletons because for each of them only one letter and only one case are allowed. All other intersections are empty because as soon as we prohibit 2 letters and one case or 2 cases or one letter, then we will have no strings which satisfy those conditions. So our inclusion-exclusion formula says that the cardinality of the union of x, y, z, and u is equal to the sum of the cardinalities of individual components, but each of them has cardinality to the power n, and we have 4 sets, so 4 times 2 to the power n, minus 4 times the cardinality of those singleton intersections, which is just 4. Therefore, for our fixed n, the number of valid passwords of length n are 4 to the power n minus 4 times 2 to the power n plus 4. And to get the final answer, we need to add this up over n equal to 8, 9, and 10. So this is the final formula, and one can compute that it evaluates to the number 1,369,100 valid passwords. This completes solution of problem 3. Problem 4. A round table has 6 numbered seats. In how many different ways can 3 couples be placed at this table such that no one sits next to one's partner? Solution. We have 6 seats and 6 people, so the total number of possible placements is 6 factorial, which is 720. Let us now compute the number of forbidden placements. Call our couples A, B, and C, and let X be a non-empty subset of the set of all couples. So let us compute the number of placements in which all couples in X violate our condition. That means that the 2 people in each of these couples sit next to each other. Let the cardinality of X be K, and then K is of course either 1 or 2 or 3. So if we treat each couple as one unit, so we need to place couples in X, so these are units, and then all other people as separate units. So we need to place 6 minus k units around our table. So we can order 6 minus k units in 6 minus k factorial different ways, but we are supposed to place them around a round table, so we need to adjust for rotations. So in order to adjust for rotations, we should divide by their number, because as many units, as many times you can rotate them around the table. So this gives us 6 minus k minus 1 factorial different ways. Then, if we have this rotational placement, we can choose a seat for one particular person, and then everyone else gets seats automatically because the order is fixed. And of course, we need to take into account that when we place a unit which contains two people, there are two ways to place them next to each other. So, by the rule of product, this gives us 2 to the power k times 6 minus k minus 1 factorial different placements, where the couples in X definitely violate the condition of our problem. Now we can use inclusion-exclusion. There are 3 choose k ways to choose X of size k out of the set with 3 elements A, B, and C. So by the inclusion-exclusion formula, the total number of forbidden placements is the sum over all k from 1 to 3 minus 1 to the power k plus 1 times 3 choose k times our number 2 to the power k times 6 minus k minus 1 factorial. And it is easy to compute that this evaluates to the number 528. So these are the forbidden placements. There are 720 placements in total, so the number of allowed placements is their difference, which is 192. And that's the solution to our problem. Problem 5. Compute the Möbius function for the poset given by the following Hasse diagram and determine mu of 2, 5. So we have a poset with the minimal element 1, then we have 2 above 1, then we have 3 above 2 and 4 above 2, but 4 is not above 3. 5 is above 3 and above 4, and 6 is above 5. That's the Hasse diagram. The zeta function for this poset is given by the following matrix. So we have 6 times 6 matrix, upper triangular, and the only thing which is not connected in this Hasse diagram is that 4 is not above 3 and 3 is not above 4. So in this matrix, the element in row 3 and column 4 must be 0. And all other upper diagonal elements are 1, and the elements on the diagonal are 1. So that's the zeta function of this poset. It is very easy to compute the inverse of this matrix, and it is given by the following matrix: 1 minus 1, 0, 0, 0, 0, 0, 1 minus 1 minus 1, 1, 0, 0, 0, 1, 0 minus 1, 0, 0, 0, 0, 1 minus 1, 0, 0, 0, 0, 0, 1 minus 1, 0, 0, 0, 0, 0, 1. That's the inverse of the previous matrix, and this matrix corresponds to the Möbius function. So for example, mu of 1, 2 is minus 1, mu of 1, 3 is 0, and so on. Our problem asked for mu of 2, 5, row 2, column 5. This is this one. So mu of 2, 5 is 1. It should be 1 here. This completes the solution to problem 5. Problem 6. Let x and y be finite posets. Consider the Cartesian product of x and y as a poset with respect to the partial order, which is given by comparing the first elements and then comparing the second elements in our pairs. So a pair is less than or equal than the other pair if and only if the first element is less than or equal to the first element and the second element is less than or equal to the second element. Prove that the Möbius function for this product equals the product of the Möbius functions. And this means the following. So the Möbius function for x times y evaluated at a, u, b, v is equal to mu of x of a, b times mu of y, u, v, if a is less than or equal to b and u is less than or equal to v, and 0 otherwise. Solution. Let us start by noting that the zeta function for our direct product of posets clearly satisfies a similar property. So the zeta function for the direct product evaluated at a, u, b, v equals zeta of x at the pair a, b times zeta of y at the pair u, v if a and b are related and u and v are related, and 0 otherwise. So what we need to prove that the matrix for the zeta is inverse to the matrix for the mu from the formulation of our problem. And this is equivalent to the following equality. But if we have two elements, a, u and c, w, in our direct product, then the Kronecker delta function applied to the pair of these elements equals the sum over all intermediate elements b, v between a, u and c, w, and then we should take the value of the mu function for our direct product at the pair a, u and b, v. So we should add up these values of the mu function over all intermediate elements. So if a, u is equal to c, w, then the right-hand side has just one summand. That's b, v equal to this common a, u or c, w. And then, of course, in this summand, both factors are 1 from this definition of the mu function. So the value is 1 and the equality holds. If a, u is strictly smaller than c, w, then we can write the right-hand side as the sum over all b between a and c and over all v between u and w, mu x of a, b, mu y of u, v. That's because of the definition of our mu function for the product of our posets. We can further rewrite this as a product of two sums. The first sum is a sum over all b between a and c, mu x evaluated at a, b, and then the sum over all v between u and w, mu y evaluated at u, v. Since a, u is strictly smaller than c, w, we must either have that a is strictly smaller than b, or u must be strictly smaller than v. If a is strictly smaller than b, then the first factor is 0. If u is strictly smaller than v, then the second factor is 0. But in any case, the product is 0. And that's exactly what we needed to prove. We needed to prove that this is 0, so we proved this. This completes problem number 6. Problem 7. Consider the set of all positive integers as a poset with respect to the divisibility order. Recall that we have the Möbius function for this poset, which is given as follows. The value of mu at the pair d, n, where d is a divisor of n, is equal to -1 to the power s, in the case when n divided by d is a product of s different primes, and it is equal to 0 otherwise. Prove that Euler's function phi, which assigns to n the cardinality of the set of all elements k between 1 and n, which are coprime to n, so which do not have any common prime divisors with n, that this Euler's function phi can be expressed in the following way. So phi of n is equal to the sum over all d, the divisors of n, and then our mu function evaluated at d, n times d. Of course, this looks exactly as a usual application of the Möbius inversion formula. So the Möbius inversion to this is the following thing. So we need actually to prove that n is equal to the sum over all divisors d of n, phi of d. So let's prove this. Let d be a divisor of n. Let x sub d be the set of all elements between 1 and n, which satisfy the condition that the greatest common divisor between this element and n is equal to d. So now, if we have an element in this set xd, then this element is divisible by d, so it is of the form d times r for some r. Then this r is, of course, between 1 and n divided by d, and r must be coprime to n divided by d, because d is the greatest common divisor between our k and n. Conversely, if we have r between 1 and n divided by d, which is coprime to n divided by d, then this defines a unique k, which is equal to d times r in xd. So sending k to r is a bijection between x sub d and the set of all numbers between 1 and n divided by d that are coprime with n divided by d. And now then our formula that n is equal to the sum of phi of d over all divisors follows directly from the rule of sum. And the formula that phi of n is equal to the sum over all divisors mu d, n times d is obtained from the formula that n is equal to the sum of phi of d over all d by Möbius inversion. And this completes problem 7. Additional problems and questions. Problem question 1. In a class of 40 students, 25 study mathematics, 20 study physics. If 10 students study both subjects, how many students study neither subject? Problem question 2. Between 1 and 10,000, how many integers are divisible by either 2 or 3 or 5, but not by 7? Problem question 3. Between 1 and 10,000, how many integers are divisible by either 2 or 3 or 5, but not by 10? Problem question 4. Consider the identity function on the set of all positive integers and define g of n as the sum over all divisors d of n and then the identity applied to the divisor d, just d. So check the Möbius inversion formula that it recovers the identity function from this g. Problem question 5. Consider n underlined to the power 3 as a poset with respect to the natural order. So ABC is less than or equal to UVW if and only if A is less than or equal to U, B is less than or equal to V, and C is less than or equal to W. Describe the Möbius function for this poset. Thank you very much and see you next time.